Okay, I'm going to solve one example of using energy method, in particular Castigliano theorem for truss. So if you remember, truss is a connection of number of bars like that. So each one of these members, for example, is a truss. Okay, each one of these members is a bar, is not a beam, is a bar. So you can go only under axial compression or tension first. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 bars connected together. So in the energy method, we said that we have to find the internal energy of the total system. So if that's my system, this energy is going to be energy of bar 1, a scalar summation of internal energy, let's use Ui, internal energy of bar 2, internal energy of bar 1, plus plus internal energy of bar 8 in this particular example. Once we find internal energy, then we take derivative with respect to a force that is applied at a point. For example, here, if we apply a force P, find the internal energy, then take derivative of this with respect to P is going to give the deformation or the deflection of the system. So under that force, this truss is going to move like that. It's going to go up a little bit. This deformation delta is equal to partial summation of internal energy with respect to the load P applied there. And then we can numerically compute this. So the road path is very clear. So let's consider a system that has arbitrary n number of a truss that has n number of arbitrary number of bars members. So the internal energy total is the summation from 1 to n of bar energy, internal energy of bar I. So it's going bar 1, bar 2, bar 3 to n for total energy of the entire truss. Right? So what's the internal energy of bar I, the ith bar? We refer to this table that we drew last class, and we know that for a bar, the formula is here, internal energy. So it's equal to the force in that member square. Look, the force is not P in all members. We can find the force in each member of the truss using truss analysis, and you know how to do that. The force in that member square times the length of that bar divided by 2A plus area of section of that bar, modulo of elasticity of that bar. So everything depends on that bar. So I write here summation I from bar 1 to n. Then I use this formula. P is the load in that bar. Let's call it n because we don't want to be confused with the 1P that we use to find the deflection. So I say n, the load in that bar, instead of P you can say n, you can say F, it's just a symbol. N, load in that bar, I, bar I square, times the length of that bar divided by 2 area of that bar modulo of the elasticity of that bar. This is the internal energy of total system. Now, Castigliano theorem says deflection at a point is equal to partial UI total, the internal energy of the system with respect to the P, the load applied to that point. And this is along the load. So if you want to find deflection in X, we apply P in X. If you want to find the deflection in Y, we apply P in Y. Okay? So let's take the derivative of this with respect to P. So that's going to be the derivative inside parentheses. Instead of UI total, I use this formula. Summation I 1 to N Ni square Li 2 AI EI. Right? Okay, and then you can take this derivative inside the summation. Again, in the calculus, we had the property of interchanging the linear operator. So this linear, you can mix it, interchange it. So you can bring it in. And also, these are independent of load, applied load P. Modular velocity, error cross-section length. These are independent of P. The only thing that depends on P is the load in that member. So if we apply a P somewhere in the truss, the loading in all members is going to be a function of P, is going to be affected with P. So when I take partial derivative, I just take partial derivative, everything is constant. So let's take this in and take partial derivative of that. Then this formula becomes summation I from 1 to N, then partial derivative, partial N squared with respect to P, which become 2 Ni partial Ni partial P. This is the derivative of this term with respect to P. So you do 2N to power 1, then partial Ni with respect to P. Right? The rest Li is just constant over 2 AI EI. So as you can see, these two cancel out with this, and you get a very simple formula. So let's write it here. If you have a truss, or in better terminology, collection of bars, not beams, because this thing is pinned, right? That means that they don't accept shear force. If this was welded, then they would be bar, and they would be beam, right? So collection of bar pinned together, or truss. First thing. Then we have this formula. Delta at the point is equal to summation of I from 1 to N, Ni partial Ni partial P times Li over AI EI. So that's for arbitrary truss. The deflection at point is this formula. It's very general, very robust. You don't even need to draw free body diagram. So let's consider an example. So in this case, let's try to do this. Up here. In this case, we have a 2K force, and this one is pinned to the floor. This one is a roller. Point A, B, C. This is the simplest possible truss, 3 members. Now the question is, find delta at point C, deflection at point C. So, in order to do that, I can start from scratch from the energy method, take derivative, and then I get this. or I can just use the formula. Right? This is going to be in the appendix, in the final exam or quiz or test or whatever. So all I need is to find members, forcing each member, and the derivative of forcing each member with respect to the applied P. Now the question is, where should I apply my P? This is not a P, it's just a constant load. Well, I say, I can have this variable at the P, right? And at the end, when I want to do evaluation, then I evaluate P is equal to 2K, or my answer. Right? So the trick here is we make a variable force there. And if we have something here, the final deflection is a function of 2K. If the force was 0 here, like if you want to find deflection at some other point that you don't have force, then we say P is 0 at the end. When we do all the calculation, we say P is 0 at that point. So here, if you have P, now the objective is I need to find N and the derivative of N to P. Well, this is a very simple truss analysis problem. You already know how to do that. So let's do that. So if that's P, let's say the length of this 1 meter is 1 meter, right? If you write the joint equation for C, joint C, then you have force P and this number, let's say this is bar 1, bar 2, bar 3, right number. Then you have P, F2, F3, that's all you have at the joint. And this angle is 45. This is a different color. This angle is 45 degrees. Right? So if you write joint equation for joint C, summation of force in x0, so P plus F2 sine 45 degree is equal to 0. Summation of force in y0. Then negative F3, negative F2 cosine 45 is equal to 0. Right? Then that gives you P is equal to negative, P is the given. We solve for unknowns. Right? F1, F2, F3. So in this case, summation of force in x0, P plus F2 sine 45, 0, negative F3, negative F2 cosine 45, 0. So we solve for F2. F2 is equal to negative P over sine 45 degree. One equation, one unknown. And then we put it here, right? Then F3 is equal to negative cosine 45 times F2. And F2 is negative P over sine 45 degree. So that's going to be positive cotangent of 45 times P. So we just one joint, we find two force in the member. So let's write it in blue color. So F2 here, F2, because I want to free up some space for the next joint. F2 is equal to negative P, F2 negative P over sine 45 degree. And F3 is positive cotangent 45 degree times P. Cosine divided by sine is cotangent, right? So we have these. Now all we need to find is to calculate F1, right? So I free up some space. just simple Truss analysis. You could alternatively first find external reactions and then immediately get these two from the joint equation here. I mean, it depends on you. So at joint A, I have, let's draw free body diagram. So you have F3, whatever it is, F1, you don't have it, and then AX, AY, right? So two component AX, AY from this, there is no moment, it's a rotor. And then F1, F3. And F3, you already have it, so check mark it. So how many unknowns do I have? 3, right? So if you write it, then you get AX plus F1 is equal to 0, AY plus F3 is equal to 0. That will give you an equation because you have F3, right? Then we get AY from this equation. So AY is a negative, the reaction at the support in the Y direction is a negative F3, negative cotton. But what about AX? Well, we don't have external reaction, so we can't find Fx, right? So what can I do? Well, I can go to joint B, right? I can go to joint B, and if I go to joint B instead of joint A, because joint A, as you can see, we have more unknowns than equation. I have to have external reaction. Well, I go to joint B, right? Now let's go to joint B. It's kind of an iterative procedure. Sometimes we don't know what joint we should check. Joint B. Then in joint B, let's draw a free body diagram. Then you have a support, coming from support BY, we don't know it. You have a F1, forcing this member, we don't know it, so put a question mark. But you have a F2 is equal to negative P over sine 45 degree. And we know it. And this angle is 45 because this is 1, this 1. This angle is 45 degree. So how many unknowns do I have? 1, 2. How many equations? 2. So I should be able to solve for F1. I don't care about BY. I don't care about supports. In the energy method, I just want force in each member and the derivative of force each member, right? So now let's go. I'll drop this cap. So let's go write the equation. Summation of force in x0. That is negative F2 cosine 45. Negative F2 cosine 45. Negative F1 is 0. And then summation of force in y give me something for by, which I don't really care. Right? All I want is F1. And this equation says F1 is equal to negative cosine 45 times F2. And F2 is negative P over sine 45. So you take it to the right side, F1 negative cosine 45, F2. And F2 from here, previous solution, negative P over sine 45. And immediately you see is cotangent 45 cosine divided by sine, cotangent 45 times P. This is F1. So let's write it here. So you write cotangent 45 degree times P. Right? So this is F1 positive and negative. So, okay, now let's free up some space because unfortunately my whiteboard is very small. Now the question is, it says find the deflection at point C. Now we use this formula. Now we have Ni, so let's make a table. So if I make a table, this is Ni, and then derivative of Ni with respect to P. Let's just fill out this column. So, and this is member. So member 1, 2, 3, right? Let's see if you can see it. Let me check the camera. Yeah, you should be able to see it. So for member 1, the force, the axial force is 1 is cotangent. Let's use a different color. Make it more visible. It's cotangent 45 degree on P. Force, axial force in member 1. Then you go to, you don't need to create a table. This just keeps you organized to expand this series. Because you can just not do the table, just write all the terms and substitute these values into it. But usually table makes your job easier. So that's the reason I draw a table. Now the derivative of this with respect to P. What's the derivative of this with respect to P? Well, it's just simple, right? Because this is a variable P. If we take derivative of this with respect to P, this is just the coefficient, so that's the derivative. So cotangent 45 degree. Then we go to member 2. The axial force is negative P over sine 45 degree. This is force in member 2. You see member 2 and 2 here. And then the derivative with respect to P is negative 1 over sine 45. The derivative of this with respect to P. It's very easy. Sometimes you get some other term, then you have to take the derivative with respect to P. But this is just simple linear, right? Now for 3 is cotangent 45 degree times P, and then the derivative with respect to P is cotangent 45. That's it. Now, all you need to do, look at this formula. You need to multiply this together. So this time this, this time this, this time this, and add them together. Right? So let's make another column. Let's extend this a little bit. And this is Ni, product of Ni times partial Ni, partial P. This product, which is this, right? So the first time become cotangent 45 degree to the second power times P. The second one become P over sine 45 degree square, and then cotangent 45 degree square times P. This is this product. Now, if I add them together, if I add this product all together and multiply by corresponding L, look, the L is different. L1, let's make a table. Let me add another column for L. So this is Li, the length of bars. For bar number 1, the length is just obviously 1 meter. For bar 2, the length is the square root of 2, because this is 1 square root of 2, right? For bar 3, the length is 1 meter, right? So all you do at the end, you multiply these together, right? Multiply these together, add them up all together, And because A is constant, the cross-sectional area or modulo of elasticity. Let's say this truss is made of the same material with the same modulo of elasticity. And it has the same cross-section each member. So you can take, this is a constant, you can take it in outside of the sum. So that's going to be this deflection at point C in this example is equal to 1 over AE, which is same for all, summation from 1 to n, ni, partial ni, partial p, li. So all you need to do, multiply this together and add them, divide by AE. That becomes the deflection. So, if I do that, I wish I could do it right here because I don't want to erase this. The deflection at point C, the final answer is 1 over AE. Again, you have A given to you in the question, modulo of elasticity. All the numerics are given to you. So 1 over AE, parentheses, now I'm going to put this sum. So I start from here, 1 times this, it is itself, cotangent 45 square times p, plus the square root of 2 times this, plus the square root of 2 times p sine 45 degree square, plus 1 times this, which is cotangent 45 degree square times p times 1 is itself. So this is sum of ni partial nip times li divided by AE. So that's your final answer. Now there is one last thing we have to do. You know that you have cross-sectional area, the numerics for that is a number, right? This is also material property, a number. You know everything is known except P. P is parameter. So what should I do? Well, P was originally 2K. So at the end, the evaluation step, here we say instead of P is equal to 2K, 2K, 2K. That gives you deflection at point C. So this is very straight, very interesting. Now we can actually do more creative problems with this. For example, let's consider that instead of fixing this to the ground and this roller on the ground, we can put it on a beam. So I can have a composite problem. I can have a beam right, and this is an I-beam. All the cross-sectional area property given, material property is given, everything given. And now for this truss, I can, instead of pinning it to wall, this was pinned to a wall, right? I can put a pin here, and I can pin it here, right? So this is one member, and then here in the middle of the web, I can have a set of rollers, and I can roller joint it to middle of the web, like that. Roller here. And then I put another bar to fix this to the pin. So basically what I did, I just mount this on a beam, right? So if I apply, a force P like that, the same problem, P is equal to 2K. Then the question is, what's the deflection of this point? That's the question. Well, the deflection of this point is not the same like this. Why? Because when you apply P here, then this beam, you see the neutral axis or elastic curve is going to go like down, like that, and then this entire thing, assembly, is going to go down. So you get something like that. This is the deflection. And also this is also deflects. So you get a skewed, this bar also deflects simultaneously while beam deflects. Everything is deflecting. Right? So this deflection, you don't, you have both X and Y deflection in Y. It's two-dimensional deflection. Now, if I ask you find the deflection only in X, and you have variable P, which at the end you make it 2K, then what should we do? Well, obviously this formula is only for bars only. Now, what we can start from scratch. Let's say the internal energy of the entire system, U total, is the internal energy of bar 1, 2, 3, right? So UI bar 1, 2, 3 plus the internal energy of the beam, because we have a beam here, and that's going to be plus integral 0 to L mx squared over 2EI dx. Now, if you look at this equation, we know that if we apply a force P here, the force in each bar, which is consequently the internal energy of each bar, is a function of P. But what about this weird integral here? Like it doesn't look right. Like it looks, okay, this equation is complicated, but it's not. If you note at this equation, the moment in beam is also a function of whatever force we have here, we apply here. And that is also a function of P. So this is also a function of P, this function of P, so we can take the root of this with respect to P to find the deflection there. But look, we are forgetting one thing. You can pause the video now and think about it. Like you need 60 minutes to figure it out. We are forgetting something. Now I'll let you guys pause the video, think about it, and then come back and check it, okay? Alright.